Didn't send me the third, the link to the third. No, to the third.
I'm doing it now then.
I think maybe you did.
No,
I didn't
probably
see
you are right.
Because it's been a crazy week, so it's possible that.
Are you at work? Are you at the university?
Yes, I'm in university.
Quite jealous me. I'm very.
Yeah, this is my office.
Nice.
Yes.
And I have to put.
So can I put it in the chat or?
Can you? Yes. Can you also send to me because otherwise.
I mean, if I can put it in the chat, you can copy it from there, or you prefer an email?
Well, if you can do both, it's great.
Okay.
And I'm putting the YouTube in the web page.
I've just sent the email.
Okay, thanks. My internet is so slow.
Hello, good afternoon.
Hi, Maisa.
Hi.
Hi.
Second, I'm putting the YouTube on the web page. Okay. Okay, it's done. Okay. So there is someone else from Barcelona. Juan, are you from? I recognize the university. Marie.
Yes, I'm here in the UB.
I'm really jealous now. I've seen beautiful. Wow.
No, but what you can see is a picture.
Yeah, I know, but it still remind me.
I'm at home now.
Yes, still, you can go if you want. It's such a beautiful place. Oh my God.
Yeah, yes, it is.
So what are you working on?
I'm doing my PhD with Alex Aro.
Yes.
Ernest Fontic.
Yes.
And also I could work with Angel.
Ah, that's great.
In a few things. And I am
good.
So interested in his work.
Yeah, of course. So very good group of people.
Yeah,
you are
really
very
nice.
well taken care. Yes, I know. Yeah, very well. Ah, okay. So this is the link. Yeah, I'm really enjoying. Last year, I stayed 3 months in Barcelona. It was a dream.
Oh yeah.
Yeah, it was a dream. I did a full. I even took Catalan courses. I went to the Centro Cívico and took courses there. So I full immersion. The Catalan courses are fantastic because they also do integration politics. They teach how people live. You know, there is how you do this in your country. Here we do this way. It's a very smart way of integrating people. It's fantastic, really.
Yeah, well, between Spain and Italy is quite. I would say it's quite similar.
But we don't have this in Italy.
No.
These courses of culture, because it's a course. Yes, I know, but I was there in the course with people from all over the world.
Yeah.
And they were making a point not only to teach the language, but to compare way of life, so people could be aware of the difference and the similarity. That's so smart, you know. It's like I wanted to write an article, but the teacher would agree, but then the pandemic exploded. So, because, you know, at that moment we heard so many things about Catalonia, separatists, but no one spoke about these ingenious and great things working there. So I thought, we should write about this and so on. But then the pandemic took over, and talking about integration of immigrants didn't seem a priority anymore.
Yeah. Apparently it's finishing now. So apparently, I mean, we are reopening bars, discotheques.
Here, no.
No, not yet.
No, and you know that in Chile, they are vaccinating better than here, but the epidemic is going faster than the vaccination. So they had to force a lockdown, because otherwise they couldn't take, it would not work. Yeah, so because it exactly depends on the variant it's circulating, you know, because they were saying that the Delta variant, that is Indian, then AstraZeneca is only one dose is only 30% efficacy, something like this. So then you have to really close everyone and vaccinating everyone before to say, you know, the percentage of vaccination is really crucial as a parameter in this case. And here we are going very slow. I mean, we're going, but it's not fast enough. And apparently, even in Chile, they are faster than us. I was listening to American TV that Vermont, 80% people vaccinated. How about there in
well,
in Spain?
Here, I mean, you mean here everybody, I think almost everybody accepts the vaccine. No one refuses. That's what you mean, right?
Yeah, but how many have been vaccinated?
It depends, because they started from old people down. So now they are vaccinating 35.
Yes, it's good.
So I'm fully vaccinated, which means I'm old. So I mean, now if you want to pretend to be young, you have to say you are not.
I got my first dose yesterday.
What did you get?
I can just cheer with one arm, because the other one I cannot move.
Yeah, what did you get?
I got Pfizer.
That's very good, very good.
Yeah, I'm happy.
Very good. Yeah.
I got Pfizer too,
Yeah, it was very easy. I got just nearby the house. I didn't have to search or anything. The first 2 blocks of the house.
Where are you? Where do you live?
In Copacabana.
Yeah. Yeah. Anyway, so actually today is the last lecture of the semester, and then we will start at the end of August with Jacqueline giving a course, a mini course on ergodic theory.
Okay.
So,
I had forgotten. It is me. Yeah.
So, you know, if your student want to learn about ergodic theory, they can come, you know, Brazilian ergodic theory, you know. They can come to listen to Jacqueline.
Subject,
Yeah. But we have specialists here, so, you know, each country sharing their special. So I'm sure that Jacqueline is very famous to be an excellent teacher among the students. So she will do a
well, let's see. Let's not do too much propaganda. Let's lower the expectations, and then from then we just have to win.
Okay. Okay. So, well, I guess we can start. Okay, so I did the YouTube. YouTube is on. I sent a message, so we can start recording. Okay, let me start recording. Okay, great. So great pleasure to have Angel with us one more for the last, unfortunately, but maybe not really the last for this semester, but in the future. I'm sure that it will be with us some other time. And please, Angel, so we're happy to have you.
Yes, so this is the last part. So in this part, we will discuss, the computation, of high order approximations to invariant manifolds of fixed point and invariant Tori, with showing the, we will see an example in which, that gives very good results. It's about capturing asteroids in the Earth Moon system. And also that it's a place where we really need to produce high order approximations to invariant manifolds, so linear approximations are not enough. At the end, I will mention a few things about parallelizing computations, because some of the algorithms can be written in a way such that they can be programmed very efficiently in parallel computers. But that will be sort of little comments at the end. I have 68 slides, but some of them I'll go very fast over them, and I've only put them in case you want to read them. Okay, so let me go back to the parametrization method. I mentioned it before, but now let's enter it. So this method, I look for the history. And it's unclear. Simon was explaining these methods in lecture in the 80s when I was a student, so I was aware of that. And also there's a paper by Franceschini and Russo 81, which they use it for a non-map. And at that time, this was only a computational tool. But it's remarkable that later on, Cabaret, Fontic, and De La Llave showed that this method is a very good tool to make theorems, to make proofs. So and they use it to prove the existence of invariant manifolds in many situations, and is still being used today to prove to make proof of existence of invariant manifolds. So here I will explain the method in algorithmic point of view. I put a reference in case you want to go deeper in it. And I will use this algorithmic point of view, this algorithmic version, to mention how it can be converted into a theorem and the hypothesis and these things. So let me start with the simplest case. So we have a fixed point with an unstable eigenvalue, and we want the invariant manifold. Okay, so the fixed point, let me call it Z0. Lambda is a real eigenvalue. I will assume it's larger than 1, for instance. And for the moment, let me assume there is an invariant manifold associated to this eigenvalue. It goes out in the direction of the eigendirection. And let's try to compute it to find it. So as usual, we'll assume everything is analytic, although the things can work with finite amount of differentiability. But to avoid technical discussions, assume everything is analytic, and that I have all hypotheses I need. I will mention the hypothesis I need later on, but let me assume everything is satisfied. So for instance, if I only have one eigenvalue larger than 1, all the hypotheses I need are satisfied. I don't need anything else. Okay, so then it can be proved that this manifold exists, is analytic, so it can be written as a convergent power series with respect to a parameter. The parametrization is the one I mentioned the previous day. So when the parameter is 0, I'm at the fixed point. And it's compatible with the dynamics in the sense that if I apply the dynamics on the manifold, as the manifold is invariant, then the image of this point is another point of the manifold that is exactly lambda s. So this is the parameter. So this is also an invariant equation that the manifold has to satisfy. Oops. And the idea is to find the manifold is to find these coefficients A by trying to solve this equation order by order. This is a natural trick. Even in differential equations, one of the first methods to solve differential equations is by power series. You write the power series of the solution, and you force the expansion to satisfy the differential equation, and you find the coefficients. So it's the same game. Nothing. Well, so it's obvious that because of this condition, A0 is Z0. That's obvious. And it's also obvious, I won't discuss it, that A1 is which is the tangent direction, is the eigenvector corresponding to the eigenvalue lambda. So that's the linear approximation to the invariant manifold that we discussed the previous days. So let me discuss second degree. I mean, I could go straight to degree m, but let me do second degree to simplify the calculations. So, okay, let me write it. That would be, I mean, with this, I mean expansion truncated to second degree. So that's the expansion. So A0 is known, A1 is known, A2 is unknown. So that's to make clear what we know and what we don't know. So, well, let's impose in various conditions. So the first, I have to put F into the map. So let me use Taylor. I'm doing Taylor on the known point, which is this, A0, A1 are known. So that's the F plus the differential plus the remainder, classical. So I will skip third order terms because I want to find second order. So when I'm expanding, everything of degree higher than 2 will be put it in that box. It means I'm ignoring it. So, okay, the second step is to realize that this is irrelevant, because that term contributes to third order of higher. So I can put it like this. Yeah. Then now let's go for this part. In this part, here there's a, let's assume I can do this. I mean, a natural question is, well, F is a map. We don't know which map. So can you really compute this? Can you really compute, I mean, this is a, S is not a number, is a symbol, is a parameter. So can you compute that? Well, let's assume I can. Okay, then I'll discuss how to do it. So, well, if I compute that up to second order, because I mean, of course, this will be a full series, but I only tested up to second order. So, well, because this satisfies the invariant condition up to first order, this will be exactly this, plus a second degree term that I have to write it because I'm working up to second degree term. And the third term coming from here is inside that box, so I don't care. That part is the same. Okay. Here, let me recall, this A2 is unknown, is what I'm looking for. B2 is known, okay, because it's A0 is known, A1 is known, F is known, and that's the expansion. So that's something, in principle, I could compute. So maybe you don't know how to compute B2, but I'll explain that later. But I want to make clear that B2 is known. Because B2 is known, let me do the following. The invariant condition is that this, so let me go for a moment back, is that's the invariance condition. So this has to be equal to this. Okay, what's this? Well, that's immediate to write. So here we have it. And then this thing here has to be equal to this thing here. We simply, I mean, here everything is known except A2. So let's rearrange the equations, and that's what we got. Okay, that's the equation that A2 satisfies. B2 is known, lambda is known, A0 is known, so everything is known. So, okay, in order to have A2 determined, I need this system to have a solution. Yeah. But, and of course, that depends if lambda square is in the kernel of this matrix or not. This is one of these kind of conditions I was asking here. Okay, so I said I need some conditions. That's the condition I need. But obviously, if lambda is the only eigenvalue larger than 1, this condition is satisfied. So I don't have to. I don't have to worry about it. Okay. Well, I can go up to any order like this. So okay. So assume that I have computed the manifold up to order m-1, and I want to find order m. So this means that's the manifold I have. Sorry, there's a typo here. I've just realized this one is not there, has not. I mean, I'll erase it. Okay, so no, and the minus. So I don't know what kind of mistake I did. Well, it doesn't matter. So that's the series. So forget about this part. And this is known, and this is unknown. So we do the same thing. We plug the series in the function. We expand by Taylor at the known point. That's first order, here, order higher. So in fact, the only thing that matters here is A0, because all the other terms contribute to order higher than Sm, because Sm is already multiplying this expression. And then I force this to be equal to Z of lambda S. Okay, so, and then what I get, so let me go straight, that's rearranging things. That's what I get. Again, like here, I have a condition of lambda m not being in the kernel of this matrix. But as I said before, if lambda is the only eigenvalue of f, which is larger than 1, this condition is always satisfied. Okay. Well, before going with the details, so let me make a comment on the proofs. That Cabré, De La Llave, and Fontic realize is that, if this matrix is nice, and in this case, for instance, it is nice, you can bound easily this term in function of this, so that you can show that the series really converges, has some radius of convergence, and that proves the existence of the manifold. Okay, that's the idea of making proofs with this. Of course, sometimes the technical details are much complicated than that, but that's the idea. Okay, so let's go to the picky point. So the worst operation is this, is to take a power series and to plug it in our map. So you can think that our map can be even a Poincaré map, so that's not easy at all. So this is something we need some discussion. And in fact, that will be the most difficult part and the most expensive part of the computation. So let's talk about that. Oh, before I comment, because I'm just here, so let me take the occasion. Now I'll be fast with this. So I've done 1D manifolds, but I could do 2D manifolds. So I can take two eigenvectors and the two eigenvalues and to write an expansion of two symbols, of two parameters like this. That's a standard expansion. And to impose invariance condition as before. And I can play the same game, expanding with two variables and going degree by degree, homogeneous degree, and keep solving the equation. So I haven't written the details. I put a reference. So essentially, that's the kind of system that you get, similar as before. And well, you can guess that if lambda 1 and lambda 2 are different and whatever, you can have a sort of resonance in the sense that you can do some kind of Diophantine approximations of the spectrum of these by some values of that. And then you need some kind of Diophantine condition or something to control that if you want to make a proof, blah, blah. And if some of these values is exactly an eigenvalue, another eigenvalue of f, then the method stops. You cannot solve. You have zero kernel. You have kernel, non-zero kernel. So method stops. And that, in fact, it can be used to show that the manifold has only finite differentiability. And that's how you see it in the proof. Okay. Okay. So.
Can I just ask you a question?
Yeah.
That the scaling equation that you use in the previous page is the same one?
This?
No, the previous, that one. The F is the invariance equation.
Yes.
How you justify? Maybe you say why you impose this scaling.
Why I'm writing like this? You mean?
Yeah. Yes.
Okay, if you linearize at the, this is an expansion around the fixed point. If you linearize in the fixed point, the linearization, the manifold is a plane given by the two eigenvectors of eigenvalues lambda 1 and lambda 2. And if you apply the dynamics, the linear dynamics there, that's the kind of thing that happens. For the direction B1, if it's the B1 corresponds to lambda 1, you multiply by lambda 1, and by B2, you multiply by lambda 2.
You are scaling the parameters so that it's...
Well, the parametrization is made compatible with the dynamics. I'm using a parametrization, which is, that's exactly, it's the same thing I did with one, maybe it's much clearer.
Yeah. No, I understand it's the same thing. So it's just a rescaling of the parameters so that...
Yes. The parameterization of the manifold is not unique. A manifold can be parameterized in infinite ways. So, but that parameterization is very convenient because it reflects the dynamics. So these invariance conditions can be imposed very easily.
Okay. Thank you.
Yeah. So, for instance, if you want to use a map like this, that's the famous dissipative Enon map with the Enon attractor, blah, blah. This has fixed point with manifolds that, everybody that has worked in this knows those manifolds. So these manifolds were computed using this trick by Franceschini and Russo in 1981. And of course, because the map is so simple, this operation, composing, a power series with a map, here it's trivial, because when you put, instead of x a power series, you only have to square the power series, for which you have a simple formula. So you can do that very, very easy. Okay, but not all the examples are as simple as this. And I want to apply it to celestial mechanics, so I want to apply it to a Poincaré map. So I need something new. So that's the trick I need. Okay, I'll explain the main idea. So first, a definition. So I will, instead of derivatives, I will use normalized derivatives, which is simply this, normalized by a factorial. So in fact, they are the coefficients of Taylor polynomials. That's what it's a simple definition. Okay, so what's the idea? Okay, imagine I want to compute the power expansion of this function at this point. That's very easy. All the students here know how to do it. Okay, so it's like a first year calculus class, you take derivatives and you expand. Okay, but let me do it in a slightly different way. So let me take this value for x1 is 1 plus s1. This one is this one, and s1 is a symbol, a letter, does not have any value. And let me take this value for x2. This is 2 plus s2. So it's again a symbol, a letter. If you want to think of something, think of a very, very small infinitesimal value. Okay? So, and now let me plug these values in the function and let me operate, simply operate. Okay, numerator is very easy. That's what you get. Denominator is very easy. Let me make a comment. This thing here is the power expansion of this product at the point 1, 2. Do you agree with that? Yeah, right? Okay, now I have the quotient. Okay, very simple idea. This was known to Euler several centuries ago. Okay, but so imagine I have a quotient. These are polynomials of homogeneous polynomials of degree 0, 1, n, 0, 1, n. I know p's and no q's and no r's. Okay, to find this expansion, I pass this thing multiplying. That's this. I do the multiplications. I equate. I equate equal degrees, and I obtain a recursive formula for these things. So this is known to Euler. So, well, I can use this formula to do this quotient. So that's what I get. Okay, this is the power expansion up to degree 2, because I work up to degree 2, of this function at this point. And I've done it without doing without taking a single derivative. Okay, so that's very nice, because if I explain a computer that it should operate this way in power series instead with numbers, for every calculation I do, I will obtain the power expansion of the result with respect to the initial data, which is a fantastic idea. Okay, let me go on. So in general, here I've only discussed the quotient, but you can ask about other things. Okay, so as a reference about these things, I'm going to say, this goes back to Euler. Well, there's this book, the reference at the end, so you have the things. So, well, here I've written a little discussion of formal power series arithmetics. So the basic operations are very simple. And if you want to perform different operations like the square root, here I take alpha 1/2, but cubic root, alpha 1 cube, or any power different from 0 and 1, which are trivial. So to find a formula to compute C, that's quite simple. It can be done in several ways, but a simple one is to take derivatives, both sides. So let me simplify, so I get this. And then the good thing about this expression, that's why I've taken derivatives, is that there's no power. It's only products. And I know how to handle products. So I can expand, multiply, solve, and I find the solution. I'm not stopping with the details, but that's simple algebra. I mean, operating expansions. Okay, this can be applied to compute not power to alpha, but to any function that satisfies a very simple differential equation. This includes the logarithm, exponential, trigonometry, blah, blah. Okay. So, I mean, when I'm applying this technique, what I'm doing is that if A is a power series, you can think of A as a function codified through their derivatives. Usually we call them jets to the set of derivatives of a function at a point. Okay. So when I'm computing this with the previous technique, what I'm telling you is the set of derivatives of HA coming from the derivatives, the jet of derivatives of A. So that's why we call that jet transport or transport of derivatives through the operations. That's a concept thing. The same thing works with several variables. Let me skip it. So I mean, if you believed it works with one, with several, so that let me skip it. So the idea is that once we have all these things programmed, because they are not difficult to program, you can go to your computer and replace your arithmetic by a series arithmetic. And then, if you had a program that computed a result as a function of initial data, now this program computes the power expansion of the result with respect to the initial data. And this has many applications. So if this program includes a numerical integration of the differential equation, then you compute the power expansion of the final point of an orbit with respect to the initial point in the orbit, which is also a fantastic tool. Okay. So let me keep going. So this is what I've just said. So in the sense that if this is a flow at some time t, and I have a code that computes this flow starting at the point x0 up to some time t, then if instead of x0 I put this, well, this is a vector of symbols, my program produces a power expansion of the result. Okay, I mean, this can be seen as an extension of phase space, including derivatives, blah, blah. Well, Poincare sections. Well, that's a very tricky thing. So, I mean, this is one of the parts I will pass very fast. I've written it in case you want to read it, because, I mean, that needs, some time to assimilate, at least the first time you see it. So I've written it. So I will only explain the idea. Okay, but I mean, feel free to ask another day or something. So the idea is the following. So let me tell you the problem. Let me go to this plot. So this is a Poincare section. That's the sigma. Let me call it sigma. Here is your orbit that arrives. This is a spatial Poincare section that arrives and cuts the section. So you stop. That's the point. So this point is the image. But the point is that during this integration, you are propagating not only the orbit, but also the Taylor expansion of the actual point with respect to the initial condition. You are propagating the whole thing. So when you stop here, your Taylor expansion, it is not inside sigma. It's in the space, but not inside sigma. The reason is that the time to arrive to the section depends on the point. Okay. So when you have a Poincare sections and you integrate and you give a complete turn and you come back, if you change the point, the flying time is different in general. So when you have a power series, and you're not a power series, depending on the value you want to give to the power series, the flying time will be different. And that's the problem you have. So how do we solve that? And that's the complex part in the thing that you need to think. Is that, well, the integration time will also be a power series that will depend on the point. Okay, so that's not easy to see the first time. It took me a while to realize things were like that. That's not easy at all. And but once you realize and you understand the reason, then, and I will also skip the details, is a matter of plugging expansions That's the plugging of the expansion. Let me skip it. There's nothing particularly difficult if the concepts are clear. It's manipulating of power series. And so you find a way of computing these corrections in the time and etc. That's high order, the same thing, how you correct the time. So, and then here I've written a small summary of how to do it in case somebody wants to. So let me skip it. Okay, it's well, application. Let me do first a trivial one, but it's nice. So Henon-Hiles is a Hamiltonian. Sorry, a typo. I also correct it. A Hamiltonian model that was proposed for some problem of galactic dynamics. So it's a 2 degrees of freedom Hamiltonian system. That's very simple. And is one of the first examples, it was raised by Henon, of chaos in Hamiltonian mechanics. So everybody, I think, has seen phase space of this. So usually it's this Poincare section, blah, blah. Okay. So what I will do, I will fix an energy level. I will find 3 fixed points in the energy level. Fixed energy level, Poincare section, and I'll find 3 points in the Poincare section that come back to themselves. So they are periodic orbits. They are unstable, and I look for the manifolds. So let me put a plot. This is to relax. Okay, that's so I don't know if the plot is big enough in your screens. Maybe depending on the resolutions. So let me try. I don't know if that helps to see the details. But now I'll explain with the mouse. Here there's a fixed point, which is an hyperbolic periodic orbit. Here there's another one. And here there's a third one, which is in fact corresponds to the first due to asymmetry of the model. Oh, you clearly see the asymmetry of the model in the plots. Okay, so for each point, we have computed the invariant manifold, the power expansion up to degree 16. So this is P1, P2, and P3. So this is the unstable and unstable for each. So they can be plotted very easily because you have a power expansion of high order, which is valid up to some distance. And from that distance on, it's very easy to do some propagation of the manifold to make the drawing. So you see, well, the source of the chaos that corresponds to homoclinic, you have homoclinic and heteroclinic intersections that, this is only a nice example. I don't pretend to have an application, but it's an example of what you can do with this kind of machineries. So let me jump to a serious application. That's the one I am interested, which is to capture asteroids. What's that? So, well, asteroids are full of rare materials. Gold is the cheapest thing you can find there. So iridium, platinum, wolframium. So the reason is that, well, all these metals on Earth are, let's say, in the nucleus, because they weight a lot. So when Earth forms, they tend to go. Because they weight a lot, so they go inside. But and so they are rare in the surface where we are. So we have to dig to find them, and there's only a little part of them. But asteroids are full of them. Okay. So, well, how we can get them from there? Well, essentially there are 2 options. Send a robot to do the mining and to bring back. That's difficult because the robot is on its own, in the sense that if the asteroid is, I don't know, half an hour away with respect, with the speed of light, if the light tries half an hour or I don't know, or 10 minutes to travel, makes very difficult to operate the robot from Earth. It has to be autonomous if you want to be efficient. Yeah, so that's a complicated thing. Or to attach some propulsion system and to push it, so bring it inside the airborne system, where the mining can be done very, very much easier. So I will focus on the second. So it is technically difficult. You have to send the engine attached to the asteroid to push, blah, blah. There's a family of asteroids which are called near-Earth asteroids, that they, from time to time, they pass close to the Earth because they have this kind of trajectory. Their orbit is similar to the Earth. So the Earth targets to do that in a first version. Okay. Well, what I will discuss is how to capture near L3. I mean, this is a point we already discussed last day. So L3 has a structure of invariant Tori invariant manifolds that connect Earth and Moon, and it's the path for rocks. It could be one of the paths for rocks for Moon to arrive to the Earth. But another piece of the manifolds goes outside the Earth-Moon system. So it's a potential tool to study, I mean, to do this kind of capture. Okay. So, well, that's simply to recall the bicircular problem, Earth-Moon, that's L3. That's the family of tori we discussed. I mean, this plot is from Tuesday talk. So this is L3, that's Earth, and this is the invariant curves. All these invariant curves, this is not periodic orbits, but invariant curves, they have tori. Doesn't the Poincare map. Okay. And they have saddle type, they have manifolds. This is the manifolds, those manifolds are the ones that connect Earth and Moon. Okay. So we have to compute the manifolds. Well, that's a bit different because this is not a point, this is a torus. Okay, it's an invariant curve of a map. So in principle, a map, I mean, a manifold can be expanded by, not by Taylor, because you have the angle, but by Taylor Fourier in this way. That's a standard way of expanding these kind of functions. And well, let's try to find these coefficients of the parametrization, which are functions that we will think of Fourier series. Okay. So, well, this first part is the torus, the invariant curve itself. This is something we already discussed how it's computed on Tuesday. And this is the unstable direction that we only compute on Tuesday. I mean, in fact, this first part, this is the linear approximation to the invariant manifold. Okay, and that's what we use. But now we'll need more. I will explain later why we need more. Okay, so how do we do that? Well, we impose invariance because that's the only, that's the only thing, the only condition we have. So if I have a point in the manifold, when I apply my dynamics, well, on the manifold, I should expand by a factor of lambda in and out, depending if it's stable or unstable. And I have to rotate because that corresponds to the dynamics on the torus. So the manifold, you can think of a cylinder, and the dynamics is to move sort of spiraling and moving in or out. Okay, that's okay. So, well, let's play the same game as before. So in principle, I will need to expand that. So let me write it this way. Let me truncate up to order m. I will straight go to degree m. I won't do degree 2. I mean, I did it because it was the first example. So now we're all experts. So I can jump directly to degree m. So this means I've computed A0, am minus 1, and I want to find am. Well, it's the same trick. I apply the map. I do a Taylor expansion. So I expand in this place because this is a point I know. That's the differential, that's the correction, that's high order. This trick here, so I can replace this by A0. That's because all other terms that are not I0 produce order higher than m. That is for the same reason I discussed. And then I have to equate the expansions. Well, as before, I mean, this term here, which is that here, produces that. And that is because this is the invariant manifold up to degree m minus 1. So it already satisfies this condition. And degree m is something I have to compute. But it's something that only depends on this, so I can compute. Maybe it's complicated. Later we talk about that a bit, but it's something I can compute. So then, proceeding as before, I can equate this thing with this, and well, working the equation, that's the condition you get, that's the condition we get, that can be rewritten very easily as this. This is an operator that corresponds for this rotation. This means this is a linear operator that rotates. So that's the equation, which is very similar. I mean, with the invariant manifolds of a fixed point, we didn't have the angle, and this was the identity. So now we have the angle, so these are functions, periodic functions, and then here I have this operator. Okay, but this is a linear system in infinite dimensions in phase space. But if I work with Fourier series and I truncate them, I mean, up to sufficiently high order, this is a finite system that I could solve in principle, so I can find A. Okay, that's of course there's some generic conditions of non-resonance that has to be satisfied, but let me skip them. I mean, if they are not satisfied, you will discover when you try to solve it, because you will not be able to. You will have kernel here. So and then determine this AM in a unique way. So, well, this is a simple comment. This is valid for stable and unstable, but usually for stable, I mean, we apply the inverse map. This is to reduce the amount of error. Okay. Okay, so that's a summary of the algorithm. So in principle, the only thing that here I'm not mentioning is how we handle the angles. So, well, there's an equivalence that it's, I mean, if you have studied a bit of Fourier series or Fourier transforms, I mean, there's an equivalent between polynomial trigonometric, which is a truncated Fourier series, and a table of value of this Fourier series. There's an, I mean, you can go from the polynomial to the coefficients by evaluation, and from the evaluation to the coefficients by a Fourier transform. Okay, there's an equivalent, you can go back and forth. So this means that in order to work with Fourier series, I will prefer to work with values. So I will pass to the values, and that's the trick to be able to do the computation. So let me go fast. I will skip it, but I will simply want to, I mean, this is a technical part. I mean, I usually insist that, I mean, if you understand the concepts, then the technical part is a matter of losing some time with pen and paper, and it works. I mean, but when you don't understand the concepts, there's nothing to do with pen and paper. Okay, so I'll try to. Okay, fundamental cylinder. This is a concept I already explained on Tuesday. So on Tuesday, the fundamental cylinder was a, let's say, coming from the linear approximation. Now it comes from the nonlinear one. So it's essentially is the same. So it's a piece of the manifolds in a like a piece of cylinder. Okay, that I have it in a form of a power expansion. Okay, I can parameterize it in a nice way, blah blah. No problem. So, and now it comes the need of the higher order expansion. Okay. So what do we do? Sorry. Okay.
I think Stefanella dropped it. Was just this.
Oh, so should I wait or?
I don't know. I guess you try to come back by her phone or something.
Okay. Okay. So that then I
can continue. Going. Yes.
I can go. So it is recorded. So, well, so then I mean, what we do is similarly as we do with the lunar rocks, is to take a measure of points on the fundamental cylinder and to launch orbits and compare where these orbits go with respect to the position of the asteroid. Okay, that's what we want to do, because we want to capture the asteroid using the manifolds. So, well, this is a little example of, oh yes, that's I should have said that before. That's an example of the amount of computations we need. So so this is a parameter for the family of invariant curves. That is the unstable eigenvalue, and that's the number of Fourier modes I use for the torus, and that is the number of Fourier. I mean, the number of Fourier modes I use degree by degree, it might changes because I mean maybe the manifold is very rounded. But when you go to high degree, they start being twisted, so you need more Fourier modes. So when you are close to L3, this does not happen. So I mean, that's degree 0, degree 16. You have the same number of Fourier modes. But and also, I mean, when you start moving away, in fact, you are approaching a bit the Earth. So the number of Fourier modes needed for high order increases. Okay. That's the parameter we use for the fundamental cylinder, how far we take it from the torus. Okay, so here is the key point. Yeah. So what happens when you propagate the points in the manifold and you compare with the asteroid? Okay, as you can guess, I mean, the manifold does not go through the position of the asteroid. That does not happen. I mean, because otherwise the asteroid would be already on the manifold and would arrive to L3, and that does not happen. Okay, what happens is that at some point, at some time, if you look at the XY coordinates of the manifold and the XY coordinates of the asteroid, they do coincide. I mean, the manifold goes over the asteroid in positions. That makes sense. I mean, simply the asteroid is in that place, but it does not have the right velocity to be in the manifold. It has another velocity. So it's different place in phase of space, but same place in position to space. Okay. Well, as we launch points on the fundamental cylinder, these orbits, they don't really reach the asteroid, but they come close from time to time. So we have to do a Newton method and to refine. So we want to find exactly which point in the manifold arrives exactly to the asteroid. Okay, so that's the condition. So this is the initial date. I mean, that's the point in the orbit. That's, let's say, the starting point integrated up to the final time. And we want, that's the position of the asteroid. So we want these to coincide. So we have to find theta and tau. This is the two coordinates of the fundamental cylinder, the angular coordinate and the, let's say, the distance over the manifold coordinate. So we have to find them such that they arrive to the asteroid. And we have guesses because we have used a mesh of thetas and tau, and we have found some of them that get close. So then, well, this is two equations because we are equating in positions and two unknowns. So, well, we can do a Newton method, that chain rule, and that's it. Well, it happens that if you use the linear approximation for the linear method, your fundamental cylinder is very, very close to the torus. That's natural, okay? So this flying time to the asteroid is very long because you spend a lot of time near the torus until you don't move away because you start very close to it. And then all these matrices has huge number in sides, and all this is ill-conditioned. So you have problems to solve this with a decent degree of accuracy. Okay. On the other hand, if the manifold is represented up to high order, then the fundamental cylinder is far away from the torus, is more far away, and the flying time is much lower. So these numbers in this system are reasonable. Everything is well behaved. So you can solve and find the trajectory, the point, theta tau point is a point in the manifold that exactly arrives to the asteroid. Okay, that's why we need the manifold. Okay, that's the comment I was saying in a written form. So let's look a bit at the results. So I will give a short summary of the results. The full results are in this preprint. So we have taken this asteroid. This is a near-Earth asteroid that's, let's say, famous one in the community. It has been used in many studies, and in 2006, it really, in fact, it entered the Earth-Moon system, stayed for a while, and went away. Okay, so we have taken, we took I mean, there's lots of data about this asteroid, so that's the one we have used. So let's show what's this. So let me explain what's this. So this is a fundamental cylinder. Okay, so this is the angle 0 to pi. This is the around the curve, and this is the length, the height of the fundamental cylinder scaled to 1. Okay, it's not 1 in fact, but we scale it to 1 to make a nice plot. So for every point in the mesh we have used, every point in this square, we integrate and we put a color that indicates how close the orbit is or passes near the asteroid. So we're using the asteroid where it was at that date. Okay. So, and this is the distance in kilometers. So the darker, the better. Okay. So this is for several asteroids, sorry, for several tori, 6. So we see that as we move in the family of tori, the plot changes a bit. And there are clearly interesting regions, these darker regions here. Here it's very dark, so it's very close. So they are interesting for a potential capture. Another interesting value is how different the velocities are at that in those points when you approach the asteroid. If the velocities are very, very different, it's going to be difficult and expensive to capture it. But if the difference is lower, it will be easier. Okay. So then there's the same plot, but comparing velocities. Okay, so I can I've adjusted the slides so I can do this. That's positions and that's velocities. Okay, as before, the darker the better. It means it's okay. So well, I mean, if you look at this dark here, there are dark regions, usually these dark blue regions, and here it's, well, in some places it's also blue. So it means the velocity is not very high. Okay. Well, that we can refine. That's an example. Oh, okay, so let me mention something to explain this. So there's not a unique minima, there are several. And that's because, I mean, the manifold, think of a cylinder in phase space, but as we look at the manifold on position space, we are sort of compressing into a plane. And if the manifold goes over a XY coordinate, in fact, maybe it goes over in 2 points because it was a cylinder, but I mean, as it is compressed into the plane, maybe that happens. And if the manifold has been being several turns and has been deformed, when you compress it into the plane, maybe there are several points. Okay, so there are several minima. So here we took 4. That's the tori for the different. The important parameter is the delta V. That's the difference in velocities. Okay. So this means this is quite high. Okay, it's not. I mean, it could be worse. It's not. But it's quite high in meters per second. This means that if when in that moment I was able to change the velocity of the asteroid by this, it would be captured. Okay, that's a simulation of this. Okay, that's this red cross is the position of the asteroid. We have 4 trajectories. They correspond to the 4 minima I was discussing. So here simply I change the velocity of the asteroid by the previous amount. I give the asteroid a quick, and I let it fly freely. So this is moon, this is Earth. So it revolves the moon, and then finally it tends to the invariant torus. So I mean, this is integrated for a while, but well, this is a stable manifold. You go against the torus, so you stay there moving around. Eventually, you will go away because we are not on the torus with 0 R. Okay. So well, once you have seen the game, you can play with other moments, because I mean, one thing I did here is to fix the moment of capture. So I've chosen, I want to capture in a very concrete date, but I can try another date. Maybe I have better conditions. And for instance, that's much better. Okay, that's the plots of positions of velocities. Here you have dark areas. They are small, but they are there, and also they correspond to small velocities. So we are chosen to minima, and here the delta V, the difference in velocities, is of 20 meters per second, which is very low. Okay, I mean, I know 20 meters per second. I mean, it can be difficult sometimes, but it's very low compared with other studies. And that's a simulation of the capture. So the asteroid, in fact, is far away. It's not as close as the previous one. That's the position. So here we give it a kick of this amount. So we do it for the 2. We are chosen one. This is 3 torus. So that's the path it gives. And then here, because the scale is not very good, but you see that the trajectory starts moving, I mean, revolving, is because it's going against the torus. Okay, that's the kind of dynamics. So that's it. So to end, a few words on parallel computations. I mean, there are cases in which these computations can be very, very demanding. For instance, in this case, my story were invariant curves. Invariant curve is a quite simple object. But in other situations, the tori, even in the Poincare section, it can be a 2 torus, 3 torus, 4 torus, or even higher. And then when you expand this in Fourier series, you get 1,000 or millions of Fourier terms. And then you have the expansion, so that thing simply explodes. Okay. So in that case, we will use different algorithms. So in principle, I mean, I will not discuss them. I mean, I will simply make you aware that for a more complicated situation, there are some algorithms. So I'm giving some references. But essentially, let me mention one of them, which is this. So this is an example. So that's very short, and that's the last thing. So this is a cooked example to produce a difficult problem. So this is a pendulum. Everybody recognizes the pendulum. And I'm adding this term. But I mean, here I have several angles. That's the frequencies. So that's a way of producing a quasi-periodic forcing with several frequencies. And then the point is to see what happens to the upper equilibrium of the pendulum, which is unstable. And so it will become an hyperbolic torus. Okay, well, if we apply the standard machinery, it means we pass first to a map. The reason we go to a map is that the torus goes down by 1, the dimension, and that's always good. And then, well, so we have used, I mean, this is a preprint we are finishing. So I'm talking about our version of the methods. So we used 31 Fourier modes for each direction, as we are having 4 directions. This is 1,800,000 Fourier modes. And because we are in phase space of dimension 2 and we have sinus and cosinus, so that's the number of unknowns, 5 million. And well, it works. That's the result. That's the stable and unstable values of the hyperbolic torus. Here is the computing time. Simply, this is the number of processors. So we use 1 processor, 2 processors, 4, 8, 16. So you see how the time goes down. And that's for the manifolds up to degree 10. Okay. So if we use only 1 processor, it's 2 hours and a half. But well, with 16 processors, I mean, today is not so rare. I mean, if you have a friend of you is a gamer, I'm sure it has a PC with more than 16. Okay. So, well, you 2 hours and a half, they go down to 11 minutes, which is pretty reasonable. Okay. Well, so this last part, I had no time to enter into details, to simply know it exists. In case you are interested, please, you can contact me. And those are the references I mentioned during the talk, in case you want to give a look at them. That's the one of parallel computation that's in progress, but we plan to finish before going on holidays this summer. And I think that's it. Thank you very much.
Thank you. So I'm sorry I disappeared. I get kicked out from my own Zoom that continued in some mysterious way. So I don't know how this is. I am on another Zoom account because I couldn't get into mine, but it's keep going. So it's a miracle. The only thing is that we have the recording on YouTube because the other stopped. But anyway. So very interesting what I see at the end because I miss the middle part. But yeah. But anyway, so Jacqueline said that we can record from YouTube, so that's good. So we have the.
Yeah, I'll pass you the slides. So I've written a lot in the sense you can because I was planning when I realized it was too much for the hour, so I realized I prefer to write a lot and go fast so you can read them.
Yeah.
And then there's the references, and you have interest in these things, you can always contact.
Yeah. Because actually, I want the students to start to put their hands on it, you know, to redo from the beginning some simple example and how to construct this invariant manifold. So just to great. So anyone question? Sorry about the interruption, but I have questions. Public is ready. Well, let's see the chat. No? Erica, Georgia.
Excuse me,
Yeah.
I do have a question. Just
Yeah.
out of curiosity, really, would you mind going back to slide 25? I guess when you talked about the
Slide 25.
25, yeah, the sigma, I guess, right?
Yeah.
I forgot the name. Should be fine.
Sorry.
When you talked about the return time, I believe, of the orbit.
That one?
Wait a minute. Yeah, that's it. Why is it reasonable to expect that, you know, the times are going to be different for each point you take into account? I don't think I fully got it.
Yeah, that's not easy. Yeah, I already warned you. I mean, don't feel bad. I mean, it's not easy. I mean, let me try to explain. I mean, in pieces. You agree that if you have a Poincare section, I mean, a special Poincare section, you have a point, you integrate, you come back, you have a return time. But if you move the point a bit, the return time will be different. Do you agree?
Mm-hmm. Okay, agree.
Yeah. Okay, so you have your initial point written in this way. That's your initial point. Okay. Mm-hmm. So yeah. The v1, vn minus 1 are coordinates. So on the Poincare section, here assuming it's a plane to make it easy. So the coordinates are linear. Mm-hmm. Yeah. And the S1 and Sn, they are little numbers that we don't specify. They are symbols, they are letters, right?
Okay. Mm-hmm.
So when I integrate this point till it returns, I want the return, I mean, this computation to be, let's say, valid when S1 has very small values, because right. I expect this power series to be convergent, right?
Yeah, that makes sense.
But if I give S small values, I'm changing the initial point.
Okay.
And I'm telling you that I'm arriving with the same flying time. There's something fishy, you see it?
Mm-hmm, yeah. No, but I guess it makes some sense.
Yeah, it's it's not easy. You have to realize of these things. I mean, in fact, I mean, if you do it with first derivative using variational equations, maybe, I don't know if you're familiar with this, this already happens there. And they have to project the derivative when they land on the, I mean, if you have done computations with I don't know, or with Poincare section and computing the differential of the Poincare map using integrated variational equations, and then there's a step at the end, you have to project the derivative, and that's because of this thing. But they don't explain in this way.
Mm-hmm, yeah, it's really the first time I'm seeing all that, so probably that's why.
Yeah, then it's not easy.
So Anja, so you can give a good reference about this, so where they can start looking at this Poincare section.
Yes.
Well, let me. I don't know if you think we'll be selfish, but the paper we are finishing, we explain all this, yeah, because there are no references doing this up to high order. So
can you send us the paper?
Yes, it's. I mean, everything is in my webpage. Every time all my preprints, I mean, all my papers are on my webpage. I put the preprint.
Okay.
So there is already there, or will be?
No. That's. I hope it will be there in a month.
Okay. So
we are writing. I mean, it's all done. It's a matter of writing, but you know that sometimes writing.
Yes, I know. Yeah. Okay. So don't forget about us.
No. I'll send you an email to you. No, don't worry.
So there are some common questions. Kursat, you want to ask you, or you want me to read? Kursat.
Oh, let me know. I think I can read the chat.
It's from Toledo.
Well, I can ask.
Yes, please ask.
The question, I'm sorry, slides 40. I guess you were talking about the Fourier transformation, Fourier series expansion.
Slide 40.
Yeah.
Share.
But there were no negative terms in the power series expansion.
Sorry, where?
Well, there is no negative term in the power series expansion, right? Because it starts from A0. There is no negative terms.
No, that's a power series. That's a smooth functions.
I see.
I don't know if I understand the point.
I thought that you're expanding a Fourier series.
Well, with respect to theta, not with respect to sigma.
Okay.
So this is a cylinder, right? So I have the theta to move around the cylinder, and I have the sigma to move along the cylinder. And I do power expansion with respect to sigma, and I will use Fourier with respect to theta.
Okay.
Yeah.
Well, somehow I'll understand more.
So it is. So let me go to this. You remember that?
Yep.
So this is a point. That's clear, right?
Yes.
So imagine that instead of a point, you give a little turn and you do a circle.
Okay.
Then everything becomes a circle too, right?
Yes.
Another way is that, I mean, if you have a function like this, I mean, I'm trying to give you different ways of looking at this. Is that if you take this and you use power expansion, I mean, the Taylor's formula with respect to sigma, ignoring theta, you will get a power expansion with respect to sigma with coefficients depending on theta.
Yes.
And that's this is.
Got it now.
Yep.
We are not expanding Fourier series. Okay, I got it. Taylor series.
Yes, I think it's clear now. Yeah.
Yep. Thank you.
Thank you, Christoph. And then there is Banu. You want to ask?
Yeah, there was something in the yeah. I mean, this is well that to no the thesis of Daniel Perez Palau. Yeah, he used jet transport with a Poincare section, but I think it was a temporal Poincare section, if I don't remember badly. I'm not now. I'm doubting. I mean, the point.
I just looked.
Yeah.
I actually just looked at his thesis. It is a spatial section he uses. So
maybe.
If anybody is interested, I think they can do that also.
Maybe it's there.
Yeah.
This is, I mean, Daniel did the thesis here with us. So, and this is a topic we have been working for years. So, but well, I'll check it because now. So I remember he was using these tools to propagate uncertainties. That was the goal. And I thought, but maybe I'm not sure, that he wrote about about this thing, about temporal Poincare sections, not spatial. But I'll check it. Now that you mention, I'll check it.
Yeah, I think it's section 2.4 in his thesis. It seems to have some of this stuff. I guess speaking of the sections with the jet transport, I guess, of course, you first have to find the expansion of the return time to the section in terms of the parameter of the jet. But then after that, is there any restriction on the type of integrator you use to then actually propagate by a polynomial return time?
Well, you compute everything at the same time. You compute degree by degree, the expansion of the return time and the expansion of, because they go together. So you go degree by degree. And there's no, I mean, we have used Taylor, Runge-Kuttas, several Runge-Kuttas. And in fact, I mean, you can prove that's, you can convert it, that's a theorem. I mean, you can prove that you get the same results if you integrate higher order variationals with an integrator. You get the same results that if you take this same integrator and you put the jet transport on it.
Mm-hmm.
You get the same numbers with the same errors. Everything is equal.
See, and I guess so you can use any integrator even when you're integrating by a time which is itself a polynomial of S.
Well, there's a restriction with that. That is explained in the slides. I haven't, I just skip it. the point is that when you use a time step that is a power with respect to s, then the error in the numerical integrator, I mean, if you are using let's say a rungequta 4, let's say you're doing something very simple, rungequta 4. So you have an error which is h5. So when your time is a power of s, because the error is h5, you will introduce terms in s5 and higher which are wrong. Yeah, because of that. So it means you are restricted to use jet transport with orders up to 4. Because, yeah, because you're mixing the error in time and in space, I mean, somehow. So, I mean, this is something you have to be very careful with rungequtas because the order is fixed, but not with Taylor, because if you use a Taylor integrator, you can change the order very easily. It's a number, you touch the order, so you adapt to whatever you need.
I see. Yeah, I mean, I was also looking at this a little bit time ago, and I thought that probably it might be easier to like integrate by the constant time t sub 0, the first jet, and then apply a Taylor integrator to the, I guess, the terms in S.
Yeah,
like
I mean, with a Taylor, I mean, you don't have this problem simply because you can adjust the order very easily. Not, I mean, if you, yeah.
Okay, that makes sense.
Thank you.
I have a curiosity.
See, please.
Yes, how do you, if in some cases you have to use a high order for your expansions, do you have a limit for that? Not concerning time of processing, but concerning small numbers and something like that?
Well, yeah, there are limits. I mean, there are some practical limits, but I mean, you have to think that you are computing the power series of a function. That's what you are doing, to compute the power series of a function. Then, I mean, usually you have, your function is analytic, not entire, so you have a radius of convergence. And then when you get to a, let's say, a bit high order, the gain by increasing the order is very low. Because, I mean, you are accumulating against the radius of convergence. So, I mean, your practical, I don't know how to explain it, but I mean, your domain gains by very little, even if you are adding degrees and degrees, okay? Because you have a radius of convergence that bounds you. And the second thing is that if you work with double precision, so you have a 10 to minus 15, so to have lots of terms of high degree that could be useful to get an accuracy very, very high, 10 to minus 40, 50 near the origin, is useless because you work with 15 digits.
Mm-hmm.
So I mean, there's a practical limit in the sense that there's no point in going higher than some values because there's almost no gain.
Yeah, I see.
Okay?
I see.
There are some specific situations in which you can work with, I mean, extended precision arithmetics. You can work with arithmetics of 50, 100, 200 digits. And then, of course, those limits are higher. I mean, because, I mean, you want more accuracy, you want more terms, blah, blah. But at the end, you are always, I mean, accumulating against the radius of convergence. So there's no gain. I mean, to compute, I mean, sometimes to go for degree, let's say, let me exaggerate, 100 to 200, which is a lot of work, means to gain 1 over 1,000 in the distance you can move away. And that's stupid, don't do it.
Yes, certainly. And you have to use high order because you are working with L3 for L1 and L2 as the
L1 and L2
the numbers are higher, the eigenvalues are higher. Yeah.
I mean, that's because to move away from L3 it takes a lot of time.
Yeah.
And then, I mean, the integration times are very big. And then when you want to adjust the final point with respect to the initial point, that's very unstable.
Yes.
And that you solve it with a high order manifold. And in L1 and L2, which are very unstable, I mean, even with a linear approximation starting very close, you immediately are pushed away. So there you don't have this problem.
Nice. Oh, I would like to thank the lectures were very clear, very interesting, very direct to the point, very good. I would like to thank you.
Well, thank you very much.
Stefanella also.
Thank you, Marisa. Well, this is the idea, to share knowledge and to learn. Everyone share with the other, and we all learn from each other. This is the idea. Yeah, thank you very much, Andrew. It was great. And I hope now you can still make it to your son graduation. No?
Yes, I'm going now, yeah.
10 minutes. So thank you for everyone to participate to the school, to this mini course. And there are some students that will have to present, work on some paper and present at the end of July. But in general, for the rest, we resume in August with the course of Jacqueline on Introduction to Ergodic Theory. So we will send and we have at the second semester, we will have many other talks. We will have Mark Levy speaking. So we'll have, yes, we will have a lot of other interesting talk of different topics. No? Okay, so thank you, Andrew. Go to your son.
Yes.
And thank you to everyone. Thank you.
Thank you.
Bye-bye.
Thank